Hello again. We are still looking at section 4.4. We've already learned about the first fundamental theorem of calculus. I mentioned in the last video that there's a second fundamental theorem of calculus that involves those functions defined by integrals. And now we're going to sort of see what that second fundamental theorem of calculus is. But before I give you the second fundamental theorem of calculus, let's take a look at a problem like this. If capital F of x is defined as the integral from 2 to x of t squared dt, so we've got a function defined by an integral. Let's find capital F prime of x, the derivative of that function defined by an integral. Please copy that down. So I want to find the derivative of this thing, and I'm not totally sure how to deal with that. So let me take a moment and actually evaluate this integral. I can figure out this antiderivative, plug 2 into there, and then kind of make some sense out of this. Capital F of x is going to equal, well, by our first fundamental theorem of calculus, I can find my antiderivative. I'm going to get t cubed over 3 from 2 up to x. I'm going to plug in an x where the t is. I'm going to get f of x equals, why don't I write it as 1/3 x cubed minus 1/3 times 2 cubed, or f of x equals, I don't really know why I did that, 1/3 x cubed minus 8/3. This is my capital F of x. What I want to do now is find f prime of x. I want to find the derivative. You know what? I think you can do that. Take a moment, find the derivative of that thing. Derivative of 1/3 x cubed, 1/3 times 3 x squared minus 0. Capital F prime of x is x squared. The derivative of this function is just x squared. Basically, it's exactly what I had inside my integral with just an x instead of a t. Well, why is this? Because this thing over here found the antiderivative, which I did. Actually, not the antiderivative, found an antiderivative. We got a particular constant over there. And then I wanted to find the derivative, and the antiderivative and the derivative cancel each other out, just giving me the original idea back. And this is the idea behind my second fundamental theorem of calculus. It tells us how to do derivatives of these functions defined by integrals. And it's really just going to be as easy as plugging in this x where the t is. Let me write it out. Theorem. Our second fundamental theorem of calculus says the following. If f is continuous on an interval containing a, containing some constant, then if I want to do the derivative of the integral from a to x of f of t dt, this is going to equal, well, this thing over here, as I already sort of saw when I evaluated, gives me an antiderivative of f. And this thing over here says, let's find the derivative of an antiderivative of f. They're going to cancel each other out, and you're going to get little f of x, which is basically what I tried to show you in that example. If I want to find the derivative of this thing, the derivative and the integral cancel each other out, you're just going to get x squared, which means we're not going to have to go through all that work. We can just use the second fundamental theorem of calculus to do these problems quickly. Please copy that down. Next, let's see. If I want to do the derivative of the integral from 3 to x of the sine of the square root of t squared minus 5 dt. I'm going to do this by just using my second fundamental theorem of calculus that says I don't actually have to go through and find the antiderivative of this, which is good because I don't know how to find the antiderivative of this. If it was just sine of t, I could handle that, but sine is something more complicated. We haven't done the chain rule idea yet for integrals, and even after we learn that, we still won't be able to deal with this one. But I can use my second fundamental theorem of calculus that says my derivative and my integral are going to cancel each other out. My answer is going to be exactly what I had inside the integral, just with an x in place of a t. I'm going to get the sine of the square root of x squared minus 5, and that's all there is to it. And I'm always allowed to do this if I have a constant in the bottom of my integral, my variable on the top, and I'm finding the derivative of that thing. That's my second fundamental theorem of calculus. Hopefully, by the way, from the example we did on the top of the page, you see why I have two different variables here, the t inside here and the x over here, and why I'm changing the answer to x. Because over here, I integrated. I got something with t's. I plugged in x's, so now I have x's in my problem, and then I found the derivative, which will give me something with x's in there. What if I give you something like this? The derivative of the integral from x to 5 of the square root of t minus 3 dt. You are not allowed to use the second fundamental theorem of calculus right away on this, because for us to be able to use our second fundamental theorem of calculus, we have to have the constant as our lower limit of integration and the variable as the upper limit. So what can you do so you can use the second fundamental theorem of calculus? I can make this negative, and I can switch the limits of integration. I can make this negative the integral from 5 to x of the square root of t minus 3 dt. You know what? I messed this up a little bit. Don't forget the derivative operator beforehand. Well, now you go and find the derivative of that. This should hopefully give you negative the square root of x minus 3. And that's it. As long as there's a constant on the bottom of the integral, a variable on the top, and we're finding the derivative of that integral, the integral and the derivative, they cancel each other out, and you're just going to get the thing that was inside your integral with an x in place of the other variable that was there. Now, this can get a little bit more complicated. So I want to show you just a couple variations of this. Let's see. I'm going to title this A Few Variations Is that actually on the screen? No, it's not. Let's try again. A few variations. For example, the derivative of the integral from 0 to x cubed of the cosine of t dt. As is, I can't use the second fundamental theorem of calculus because this upper limit needs to be just a single variable, and here it's a more complicated function. So what we're going to do here is we're going to kind of do the whole thing out like we did for the very first example in our notes, and then we're going to see if we can kind of adapt our second fundamental theorem of calculus to let us deal with things like this. This should be the derivative of. Okay, well, let me do this thing out. Let me find the antiderivative of the cosine of t. It's going to give me the sine of t that I'm dealing with between 0 and x cubed. This is the derivative of. I'm going to plug in x cubed minus plug in 0 for the t. I get the sine of x cubed minus the sine of 0. And I might as well just rewrite that. The sine of 0 is just 0, so sine of x cubed minus 0, why don't I just say derivative of the sine of x cubed? When you do the derivative of the sine of x cubed, what rule are you going to have to use? I hope that you just said chain rule, because there's something inside my sign. The derivative of sine is cosine, we get cosine x cubed, times 3x squared because of the chain rule. If I want to do the derivative of a function defined by an integral and the upper limit is itself a function, I'm going to start by just plugging in this thing where the t is, so I get the cosine of x cubed, like I did over here. But I'm not done with that. I then need to use the chain rule and multiply by the derivative of that function that you were plugging in. Let me try to summarize this. If I want to do the derivative of the integral from a constant to not just x, but g of x of some function like this. The derivative and the integral cancel. You're going to plug this thing in where the t was. You're going to get f of g of x. By the chain rule, you then need to multiply by the derivative of g of x, so by g prime of x. We're using our chain rule here. We are first taking the derivative of the integral. They cancel. That's just our plug-in part. We're going to take the derivative of our integral. Then we're going to multiply by the derivative of g of x. Copy that down, then I'll show you a couple examples. Okay, so let's say I want to do, let's actually do the same problem we just did. If I want to do the derivative of the integral from, I'll change it, I'll make it 5 to x cubed, of the cosine of t dt. I can use this new kind of variation on the second fundamental theorem of calculus to say the derivative of the integral, they cancel out, you're going to get the cosine of x cubed. But then, because of the chain rule, I need to multiply this thing by the derivative of x cubed, so I need to multiply by 3x squared. And I should probably write it as 3x squared cosine x cubed, so it's not ambiguous at all if this is inside the cosine. Let's take a look at this one, the derivative of the integral from 2 to the sine of x of t minus 5 cubed dt. I want to find the derivative of this thing. I can use my second fundamental theorem of calculus combined with chain rule. Second fundamental theorem of calculus says the derivative and the integral, they cancel each other out. You're going to get the sine of x minus 5 cubed. By chain rule, though, now we have to multiply by the derivative of the sine of x. That's times cosine of x. There's one more variation I want to show you, but I think I'm going to hold off on that and let you try a couple of these. Can you please take out the sheet, it's handwritten, titled Section 4.4 Practice with the Second Fundamental Theorem of Calculus. I would like you right now to try problems 1 through 5. Everything but 6. And I'm just going to make the video pause. See what you can do in everything on 1 through 5. Skip 6 for the moment, and then I'll show you what happens with this. Okay, I want to find the derivative of these things. First one, f prime of x equals, well, the derivative and the integral, they cancel each other out. I'm just going to plug in the x where the t was. X squared plus 1 to the 17th. Number 2 is the same deal. Because there's just a constant on the bottom and my variable on the top, the derivative and the integral cancel. You're just going to get the cube root of x minus 1. Can't totally do that in number 3. I need to change the limit, change the order of the limits of integration. So I'm going to make this negative the integral from 10 to x of t plus 1 over t dt. I'm going to find the derivative of this thing now. I'm going to get negative, plug in the x where the t was, and we're going to get x plus 1 over x. which is fine, or negative x minus 1 over x, either way. Next one's a chain rule problem. My derivative is going to be the sine of 3x in parentheses squared. But by chain rule, I then need to multiply by the derivative of 3x, so I'm going to multiply by 3. Your answer is 3 sine 9x squared. Finally, number 5, another chain rule problem. The derivative and the integral cancel, giving you the square root of 1 minus sine squared x times the derivative of sine x times cosine x. There are some properties you can use to rewrite this. I don't really care. I'm just going to leave it like this. I'll be done. One more variation I need to show you. Back in your notes. And then we'll do number 6. Let's say I want to do the derivative of the integral from 2x to x squared of the sine of t squared dt. I can't use the second fundamental theorem of calculus right away on this because the lower limit isn't a constant, it's another function. Here's what I can do. Just go with me on this. How about I say that I know that 2x is kind of my lower limit, x squared is my upper limit. What if I say that 0 is less than 2x is less than x squared? Not necessarily always the case, but just go with me. The logic will still fit for this problem. I want to find the derivative of the integral from 2x to x squared. Rather than doing that, how about I do the integral from 0 to x squared, too much, and take away the integral from 0 to 2x. I'll be left with what I want. I can turn this problem into the derivative of the integral from 0 to x squared of the sine of t squared dt minus the integral from 0 to 2x of the sine of t squared dt by our properties of integrals. Well, now we can actually handle both of these. That first one, I'm going to use the second fundamental theorem of calculus and then chain rule. I'm going to say the sine of x squared squared, and by chain rule then times the derivative of the thing I was plugging in, so times 2x, minus the sine of 2x squared times the derivative of the thing I was plugging in, so times 2. And I can clean this up into 2x sine x to the 4th minus 2 sine 4x squared. Go back to that sheet. Try number 6. Back to that sheet. Let's see. How about I rewrite f of x as, I can always use 0 as long as it's like within, as long as plugging in 0 would still make this thing continuous, I can still do that. So how about I write this as the integral from 0 to x to the 5th of the sine of t minus 2 dt minus the integral from 0 to x squared of the sine of t minus 2 dt. Go find your derivative using second fundamental theorem of calculus and chain rule. Shouldn't have said f prime of t, should be f prime of x. I'm going to get the sine of x to the 5th minus 2. Am I still on the screen? Oh, I'm still on the screen. Good. Times the derivative of what you plugged in, so times 5x to the 4th, minus the sine of x squared minus 2 times the derivative of what you plugged in, so times 2x. I'll just make this look a little nicer, and I'm going to say 5x to the 4th sine x to the 5th minus 2 minus 2x sine x squared minus 2. And that is our second fundamental theorem of calculus. The final piece we're going to look at in section 4.4, and we're going to save that for next week's assignment, is analyzing functions defined by integrals. if I give you some f of x equals the integral from something to something else of g of x or g of t dt or something like that, how can we figure out where our function is increasing, decreasing, concave up, concave down? A lot of that story is going to sound similar to other things we've dealt with, but now that we've been able to kind of understand these functions defined by integrals, we can add a few more pieces into that. And I think that's all I'm going to say. This is going to make a whole lot more sense next week. So that's it for now.